Hello, today we are going to have the second part of our lecture on calculating the moment of inertia. In the last set of notes that I posted, we had discussed that moment of inertia is the rotational equivalent of mass, because we have agreed and already established that when an object is rotating, its energy and motion is best described by not just the mass of the particle, but the location of the particle, specifically the location of the particle as it relates to the center of rotation or the axis of rotation. So the basic equation that I gave for this moment of inertia is that moment of inertia equals the sigma sum of the mass of each particle times the radius of that particle squared. And the radius is the distance between where that particle is and the point of rotation. Be sure that your units are correct. All masses must be in kilograms and the radius must be in meters. All right, so what we did is we are going to look at problem number 2 on worksheet 7.6. We're going to do this together as a sample problem because it's a bit ambiguous the way that it is worded. It gives you 3 different scenarios. I've drawn situation 1 in pink, situation 2 in green, and situation 3 in red. And you are supposed to calculate the moment of inertia for each of those scenarios and then compare and order them from the smallest moment of inertia to the largest moment of inertia. It says there are 3 pairs of spheres that are connected by very light rods as shown in the figures. The first thing that tends to throw students off is that the phrase light rod doesn't mean that you should use your note card for a rod rotating about the center. The fact that it's light means that its mass is negligible. So we are going to treat these as point particles and use this equation up here. So let's just dive right in and get started with scenario 1. So the moment of inertia for scenario 1 would be equal to the moment of inertia for this left sphere plus the moment of inertia for the right sphere. So the moment of inertia for the left sphere is going to be a small m, because that's what they say the mass is, times the radius of r squared. mr squared. Then we have to add on the moment of inertia for the second sphere. It has a mass of m, also at a distance of r squared. So mr squared plus mr squared means that the moment of inertia for scenario 1 in total is going to be 2mr squared. And this can be a bit disconcerting because we're not actually going to plug in values here. We're just going to use variables and compare largest to smallest. So using that same logic, but looking at the middle scenario, this time, the object on the left has a mass of 2m, and it's at a distance of r over 2, or 1/2 the radius. And we still have to square that because you take the mass times the radius squared. Then we add on the second object, which has a mass of m times r over 2 squared, because it's at a distance of r over 2. All right, so now we've got to simplify and reduce this as much as possible. So we need to begin by squaring the quantities here. So if we square the quantity r over 2, that's going to turn into r squared over 4, because you square both parts. All right, so we will have r squared over 4. Now if we look at this first term here, you've got 2mr squared over 4. That can be thought of as the entire thing over the entire quantity over 4. So 2 over 4 is the same thing as 1/2. So that's going to turn into mr squared over 2. The second portion we can't really reduce. We're just going to leave it as mr squared over 4. So essentially that's like saying 1/2 mr squared plus 1/4 mr squared, and 1/2 plus 1/4 ends up being 3/4, so 3/4 mr squared. So if we look now, the moment of inertia for this middle scenario is equal to 3/4 mr squared, whereas the first one was 2mr squared. So we could already establish that situation 1, I1, is larger than I2. We now need to look at the moment of inertia for Situation 3, high 3. This time, the mass of the first object is m over 2, and its radius is 2r, but we have to square the radius according to our moment of inertia equation. The object on the right has a mass of m over 2, also at a distance of 2r. We have to square the distance. So if we square that 2r, this is going to work out to now say m over 2 times 4r squared plus m over 2, 4r squared. But we could kind of combine this 4 over 2, right? 4 over 2 is the same thing as 2, so that's going to be 2mr squared plus 2mr squared. Well, 2 plus 2 gives you 4mr squared. So now, if I were to list these out, that means that I just found that I3 is equal to 4mr squared. We said I2, whoops, let me change my color here. I2 was equal to 3/4 mr squared, and I1 was 2mr squared, and I'm supposed to arrange these from smallest to largest. So if I look at those quantities, the smallest moment of inertia is definitely the I2 because it's 3/4 the mass times the radius squared. The next largest, whoops, that was a terrible less than. The next largest is going to be I1 because it's 2mr squared. And then the largest overall will be I3, which is 4mr squared. And conceptually, if you look at this, what the problem was trying to illustrate is you might have originally thought that the green scenario would have the largest moment of inertia since it had the most massive object on the left, but actually you need to factor in that moment of inertia is not just mass, but distance from the rotation point. So for number 3, since the radius was doubled, that actually ended up winning out over the fact that the masses were smaller. So that is the actual answer for problem 2 on section 7.6. Problems 1, 3, and 4 are assigned to you tonight for homework and are much more different because this moment of inertia equation can only be used for individual particles like that you're adding together. So what happens if you have like a bowling ball or a tire or, you know, an entire plank that's rotating? That is where you have to use the note card with all of the individual equations based upon the object's shape and the axis of rotation. So let's do a problem like that, which will help you with the remainder of your homework problems. It says calculate the moment of inertia of a 14.4 kilogram solid spherical cannonball of radius 6.10 inches. Note there are 2.54 centimeters in 1 inch. So the first useful piece of information that we're given is that this has a mass of 14.4 kilograms, and kilograms is an acceptable unit of mass, so that's good. Then it says that we have a radius of 6.10 inches. Radii have to be in meters for this to make sense, so we've got to get rid of inches, go to centimeters. The conversion that they gave us is 1 inch is 2.54 centimeters, but then there are 100 centimeters in every 1 meter. So you take 6.10 times 2.54 divided by 100, and the radius ends up being 0.15494 meters. Now, we are trying to find the moment of inertia for a solid spherical cannonball. So you go to that note card that you made during the last class session, and you try to find an equation that deals with a solid spherical object rotating about its center. And when you do, it should tell you that the moment of inertia for a solid rotating sphere is equal to 2/5 mr squared. So 2/5 times the mass, which is 14.4 kilograms in this case, times the radius, which is 0.15494 meters, squared. Now, the most common pitfalls as students go to calculate this, remember it's just the radius that is squared, not the entire factor, and you need to multiply the entire factor by 2/5. If you do this properly on your calculator, this will work out to be 0.138, and the units for moment of inertia are always kilograms times meters squared. You will use this same approach for the remainder of the homework problems on section 7.6. I will tell you the last problem of the section, though, considers a bowling ball that is rotating, and it says you should consider the bowling ball essentially to be two separate pieces. You've got a hollow shell sphere on the outside, and then you have a solid sphere core. So you're going to have to calculate the moment of inertia for each of those objects, and you're going to use two different moment of inertia equations, one for a hollow sphere for the shell and one for the solid sphere core, and then you're going to have to total them up. So please feel free. I have posted pictures of those note cards on the last set of notes that I posted. Feel free to go back and reference that if you need, but I hope that this has been helpful, and now you are assigned to complete the rest of worksheet 7.6